Okay, so hello everyone, and thank you very much for attending this seminar. So it's a great pleasure to have Danielle and Frank with us today. So Danielle is the presenter, and Frank the panelist. So we're gonna start now, and so this will be recorded. And please, if you have so you can ask your questions if you have any questions. So I mean, we can unmute you, or if you prefer, you can post the question in the chat, and we can read it on your behalf. So Danielle, you have 1 hour, and after that we will have some discussions. So the recording started, so the floors is yours. Okay, the floor is yours.
Thanks so much. I'm excited to be presenting here, and thank you for the invitation. Thanks a lot to Frank for agreeing to discuss and kind of lead the discussion today. So I'm going to be presenting a paper that on the face of it has a very straightforward goal that I hope is very easy to explain, but that actually has a lot of challenges and complications along the way. This is joint work with Carol Mertens, who's at the Dallas Fed, and as a result, the usual central bank disclaimer applies. So as I think many of us in this virtual room will know, IV estimators are biased, and indeed the types of inference procedures like t-tests, walled tests will be invalid whenever the instruments are irrelevant or indeed weakly relevant. So when we have relatively little predictive power for the endogenous regressors of interest coming from the instruments. And this is a problem that's been increasingly recognized since about the mid-1990s, and we've seen a few different approaches to addressing it in the literature. So an econometrician, many econometricians would recommend just accepting that this is the case for many instruments, particularly in time series settings, and just using some sort of robust inference technique, like say an Anderson-Rubin testing. But in practice, in applied practice, in empirical work, there's a real revealed preference for pre-tests because these robust inference methods often have some limitations. So people would much rather just be able to use t-tests as they usually would, conditional on knowing that their instruments are indeed strong, being able to reject a null hypothesis of weak instruments. In particular, what has become essentially what is de facto required now in an empirical paper using instrumental variables is the Stocking-Yogo test, which has become truly seminal for weak instruments, at least in two-stage least squares estimators. This test is based on a bias criterion that assesses whether the instruments are weak enough to bias two-stage least squares to a specified extent. Now, based on this bias criterion, the authors develop critical values that can be applied for the first stage F statistic, or indeed in the case of multiple endogenous regressors for a Craig-Donald statistic. So the idea here is essentially we're determining whether the instrumental variables are weak enough for the endogenous regressors to lead to bias beyond some certain allowable extent. If the bias is too bad, we're going to reject the null hypothesis, we're going to fail to reject the null hypothesis of weak instruments, and then you'll need to either abandon those instruments entirely, which is what I fear many people do in practice, or else resort adopt some robust inference procedures. One of the key assumptions in the Stocking-Yogo paper, though, is that there's no heteroscedasticity or autocorrelation present in the data, or indeed there's no clustering structure present in the data. The errors essentially have to be, IID homoscedastic. This really unfortunately places empirical researchers in a bind, because you'd be hard pressed today to find a paper using an IV methodology that would make similarly strong assumptions on the errors when conducting inference on the structural parameters themselves. So empirical researchers often find themselves making one set of assumptions on the errors for the sake of their first stage kind of pre-test, and a different set of distributional assumptions when they actually conduct inference on the parameters of interest. So this is ideally, this is not something you'd ideally want to do. This is very much an incoherent approach to testing, which I think you actually do see quite often in the literature. Montiel, Lear, and Pfluger make some significant progress in this direction, though, proposing what they refer to as an effective F statistic. essentially the effective F statistic is a rescaled F statistic with new critical values that accounts for heteroscedasticity and autocorrelation. So far, so good. But the limitation here is that it only applies to in the case with a single endogenous regressor, which is quite limiting in terms of empirical practice. So what we're going to do in this paper is extend the Stock-Yogo test and the Montiel-Li and Pfluger tests jointly in a way that's going to allow for both heteroscedasticity and autocorrelation and multiple endogenous regressors. So it's going to be a general test. It's going to nest both of these existing tests as special cases. So there's been a lot of focus in the literature more recently on the pre-testing problem, and this is a little bit orthogonal to what we're doing today, although in simulations we will be able to speak to this problem a little bit. I note that there's a question that a lot of econometricians are asking, which is, should we be conducting these sorts of pre-tests in the first place? I think that's a big debate. That's not something that we're seeking to answer in this question, in this paper. But ultimately, we think empirical researchers are going to use pre-tests. They're using pre-tests. We prefer them to be using pre-tests that are making accurate assumptions about the error distributions. And that's what we hope to be able to facilitate with this paper. So the model here is going to use fairly standard notation, and we're not really reinventing the wheel here. Lowercase y is going to be the dependent variable. Capital Y are going to be the endogenous regressors. Beta, the structural parameters of interest. Mu are the structural errors. V are the first stage errors. Pi here are going to be the first stage coefficients on the instrument Z. We're going to have T observations. K is going to be the number of instruments. N is the number of endogenous regressors. Without loss of generality, we're going to assume that there are no exogenous regressors, right? Because we can always, using Frisch-Ward, just parcel out any exogenous regressors ahead of time. And we're going to normalize Z prime Z to have identity covariance, sample covariance matrix. So these are just just normalization, kind of standardizations up to this point. So what is the two-stage least squares estimator now? Well, the way that you kind of teach it in an undergraduate class, right? You're just regressing capital Y on Z in a first stage, then using Y hat, predicting the values Y hat, and regressing lowercase y on capital Y hat. Equivalently, and this is the form of the estimator we're going to carry throughout the paper, you're going to be basically looking at the ratio of projections through the instrumental variable Z. So we're going to look at essentially the ratio of capital Y, P, PZ, lowercase y, over the projection of capital Y, the quadratic form of the projections of Z for capital Y. So what is the weak instruments problem? Well, it's essentially what the weak instruments problem arises when that set of projections you see in the denominator is small in some sense. What this paper is about is what does it mean for this denominator to be small, and how do we assess whether this denominator is small enough to cause problems essentially in practice. So to clarify what our actual generalization is going to be, it's helpful to introduce the reduced form here. So as I'm sure many of you know, right, the reduced form is just going to be regressing lowercase y, our dependent variable, directly on the instrument Z. So this gives rise to a new error term, W, which is going to be a linear combination of V, the first stage errors, and U, the structural errors. So to make clear what our generalization is, let's assume that the rescaled sums of Z times W and Z times V are going to be asymptotically normally distributed with covariance matrix W. W here is just going to be the asymptotic covariance of the reduced form parameters reduced form coefficients estimated by OLS and the first stage OLS coefficient. So W is just a standard covariance matrix of OLS coefficient estimates. So in Stock-Yogo, this matrix W is required to have a very special form. It's required to have a Kronecker product form, which is essentially imposing the conditional homoscedasticity and no serial correlation that I mentioned before. This is kind of where the key assumption is coming in. Montiel-Li and Pfluger, on the other hand, allows W to have a more general form, but requires that N is only equal to 1. So W is always of dimension 2K by 2K. What our contribution is in this paper is to allow W to be any N plus 1K by N plus 1K matrix, essentially, where N is greater than or equal to 1. So we're relaxing these key assumptions from the two existing papers on this W matrix, either a dimensionality assumption or a structural assumption that requires this homoscedasticity. So to give you an idea of where we're going to have to go in this paper before we get kind of into the econometric weeds, the testing procedures is as follows. So we're going to be testing a null hypothesis of weak instruments being present. So we're going to do this by assessing whether the weak instrument's bias exceeds some pre-specified tolerance level tau, with the test occurring at some significance level alpha. So tau is going to be biased relative to some threshold. The default in this literature that Stock-Yogo F greater than 10 rule is based on a bias threshold of 10%. So basically, whether the bias exceeds 10% of some benchmark. So the testing procedure will require the econometrician to estimate a robust covariance matrix, which we're going to note here W hat. This is heteroscedasticity and autocorrelation robust. This is cluster robust. We're not going to kind of discuss this any further. We're going to assume you know how to consistently estimate this W matrix for your application of interest. Then the econometrician will compute a test statistic G-min, which is going to be equal to the minimum eigenvalue of a rescaled version of the denominator, so to speak, of the two-stage least squares estimator. This is also, you can review this kind of also as a rescaled Cragg-Donald statistic, which is going to look very similar to the statistic in Stock-Yogo, except for this rescaling. And we're going to come back to this particular structure of this rescaling matrix phi in a couple of slides. I'll tell you a little bit more about that special structure. Then, given tau, your tolerance level for bias, alpha, the significance level of the test, and W hat, you're going to compute a critical value from an approximate bounding distribution based on the Imhoff approximation. Now, that's a bit of a mouthful. There's a lot of different things going on inside that black box. That black box, from a user's perspective, is available on our websites in a MATLAB function. We're currently working on a Stata function that will be available to do all of this as well. Hope to have that in a couple of, another month or two's time. Essentially, there's a lot of work that goes on to make that critical value function very fast to compute in practice to maximize applied use. Finally, you're going to reject the null of weak instruments if your test statistic exceeds the critical value. So this is the structure of the test, and the remainder of the talk is going to allow us to go through constructing these various steps.
So Daniel, I guess we're going to talk about tau, right, later, no?
So tau, the tolerance level, and what it means. Yeah, when you talk about the bias criterion, I think I'll say some more about tau. But in practice, tau is just set equal to 0.1 in this literature. Of course, you can adjust that as a user, but that's kind of the norm adjusted in the publication. The norm adopted in the publication process, more or less.
So maybe I didn't get the story here, but so that level could be like the threshold that that decides whether it's like the estimator is significant or not. Maybe if you increase a bit or a little bit less or a little bit more than that threshold, you are moving from rejection to.
Yeah. So this is a question, right, of how much bias is too much bias, essentially.
Yeah.
And I think it's a hard question to. I mean, this is a hard question to answer, particularly before we see what our bias criterion is, because it's bias relative to something. So I need to discuss that before it becomes meaningful. But the level adopted in practice, and whether that should be 10%, which is de facto what the literature has adopted, I don't know a good way to answer what the right level of bias to allow for is. That's a great question, really. Anyway, to propose this test, we have to address 4 hard problems in this paper. It's not just a straightforward extension. So actually, to go exactly to the question I've just received, we have to first define what weak IV bias means in this setting, right? What is tau referring to? This is not a well-defined concept yet in this more general setting. Second, we have to argue why G-min, this test statistic we propose, is actually a sufficient test statistic for this bias criterion. Third, we actually have to work out the limiting distribution of G-min, which will turn out to be a very non-standard problem. And given that this is a pretty non-standard problem, we have to argue, if people are actually going to use this test in practice, you can't have to wait several hours each time you boot up Stata for each regression. We need to argue that we can actually compute a critical value feasibly in practice, which is actually going to turn out to dictate a significant amount of the approach that we take here. So before we get into how we're going to solve these problems, we need to set out some basic assumptions. The first is how we're going to model the weak instruments problem in this setting. So what we're going to adopt is one of the standard asymptotic embeddings in the literature to capture what is essentially a finite sample problem in an asymptotic framework. So this is going to be the local to zero asymptotic embedding. We're going to assume that pi is equal to some locality matrix C divided by square root T, where C is a fixed full rank matrix. The idea here is essentially that the entirety of that first stage coefficient matrix is local to zero. Now this is what the approach adopted by Stock and Yogo and Montioli and Pfluger. It's not the only approach in the literature to modeling weak instruments. Frank has some work thinking about instead having local to rank deficiency of 1, which is another way to think about this, where you don't think all of the instruments may be irrelevant, but asymptotically irrelevant, thinking you have a kind of smaller scale problem. This is the approach we're going to take. There are other modeling approaches, but this is consistent with Stock and Yogo and Montioli and Pfluger. The second assumption is much more notational and assuming kind of consistent estimability of a number of quantities. So essentially, we're going to assume that the sums of squared errors are going to converge in probability to their population counterparts and just denote their population counterparts with pretty standard notation. Second, we're going to formally assume that asymptotic normality that I introduced on a previous slide to illustrate our contribution, that those sums of z times w and z times v suitably scaled asymptotically normal. This is not assuming that the errors themselves are normally distributed. This is just a high-level assumption on the limiting distribution. Finally, as I've said before, w has to be consistently estimable, and we're going to partition w going forward so that w1 is the block corresponding to the reduced form parameters, and w2, which we're going to come back to most, is just going to be the asymptotic covariance of the OLS coefficients in the first stage regression. So now we can introduce the first kind of novel result in the paper, which is that under these stated assumptions, we now have a limiting distribution for the two-stage least squares estimator in this more general setting. So for those of you familiar with this literature, this is going to look relatively familiar, just a little bit more complicated. So in this literature, generally speaking, the limiting distribution of the two-stage least of the deviation between the two-stage least squares estimator and the true structural parameters, which we denote here as beta star, is a ratio of kind of products of correlated normal random variables, which is essentially what tells you that your estimate is not consistent under this weak instruments asymptotic embedding. And that's kind of the key takeaway here. The issue, kind of the novelty here, and it's not kind of significant novelty, is that the function of these normal random variables that characterizes the limiting distribution is a lot more complicated. And in particular, you see a structure that I came up when we introduced phi, that rescaling matrix a few slides ago, but I want to spend a little bit more time on. So in the denominator, you see this r prime times eta 2 prime Kronecker product with the identity matrix times R structure. This particular structure, where you basically have some matrix, Kronecker product with an identity in a quadratic form with these R matrices, is going to show up throughout the paper. So I want to explain what's going on here. So mathematically, what this is doing is, for an nk by nk matrix, computing an n by n matrix, where each entry is the trace of the k by k of each of the k by k subblocks of the nk by nk matrix. It's perhaps a peculiar mathematical structure, but that is basically, it's a matrix of traces of each of the blocks of a larger matrix. What is that doing intuitively, and why is this a structure we need to work with? Well, this turns out to be actually how you kind of keep track of the heteroscedastic structure of the error distribution here. So you can think about this, y hat, when you're thinking about the covariance matrix of all the y hats, right? That's going to be an n by n matrix. But each y hat, part of its variation, is explained by each of the k different instruments. So when you're thinking about the covariance across the y hats, you have to aggregate up over all of those k different instruments you have available as the econometrician. So this particular structure is going to basically sum up the contributions to the covariances across the different instruments predicting each of the y hats in a way that keeps track appropriately of the heteroscedasticity, autocorrelation, or cluster structure, or what have you. So this is just our structure that is accommodating heteroscedasticity and autocorrelation. So now, for those of you familiar with this literature, we can define what the concentration matrix means, what the concentration matrix is in this setting. And for those of you familiar, this is going to have a relatively familiar structure. For those of you less familiar with this literature, lambda, which is how we know our notation for the concentration matrix, is a quantitative measure of the strength of the instruments. More formally, it's how far the denominator of the two-stage least squares estimator is centered away from zero. So basically, this is just going to be rescaling of the concentration matrix you find in Stark and Yogo, where the rescaling crucially depends on this matrix phi, which is the same matrix that showed up when I defined the test statistic earlier, and has exactly that structure I defined on the last slide. Essentially, its structure is normalizing by the heteroscedasticity structure present in the data. So it turns out that lambda here is going to be identical to the concentration matrix in Stark and Yogo when the data turns out to have that special Kronecker structure that they impose. So when the data is indeed homoscedastic, concentration matrix is exactly the same as in Stark and Yogo. Similarly, when n is equal to 1, the concentration matrix exactly collapses to the formula in Montiel-Lee and Pfluger. So we're nesting each of those two tests. So now we can tackle the first of those 4 key problems that I identified a few slides ago. And that in particular is to define the bias criterion here. So what do we mean? How are we going to quantitatively measure the bias of the two-stage least squares estimator? We're going to use an L2 norm, a weighted L2 norm of the bias relative to a benchmark. So why do we need weights here? Well, think about, you've got n different endogenous regressors. They may have very different scales. You need to have a scalar measure of the bias. So you need some way to aggregate up those different entries in beta to compute, some norm of the bias. The natural way to do this is to standardize them first so they're comparable magnitude. So in Stark and Yogo, they normalize, they use weights that are going to normalize the second stage regressors to make bias comparable across the different elements in beta. And that's exactly what these weights do here. They look a little bit different because of the heteroscedasticity, but it's the exact same idea. We're just standardizing the bias across the n different variables. But the bias also needs to be relative to some benchmark. And this is where we're going to differ a little bit. So the benchmark here is equal to what we describe as the worst case two-stage least squares bias. When does this arise? Well, it's going to be the bias into the two-stage least squares estimator when pi is equal to 0. So the instruments have exactly 0 predictive power for the endogenous regressors. And the structural errors actually spanned or perfectly predictable based on the first stage errors. So this is essentially 0 relevance and as bad endogeneity as you can get. That's essentially what the worst case bias of two-stage least squares is. This is the same benchmark adopted in Montiel-Lee and Pfluger. So it's going to be a little different to the Stark and Yogo test here. Because in Stark and Yogo, you have this nice interpretation of the bias being relative to the bias of the ordinary least squares estimator. But mathematically, that just doesn't work out once you allow for heteroscedasticity and autocorrelation, which is why Montiel-Lee and Pfluger make the decision that they make, and that's why we're going to, the same reason that we're going to do this here. However, when there's a Kronecker structure for W, right, when homoscedasticity does hold, the bias criterion, and indeed this benchmark, is exactly the same as in Stark and Yogo. So then you do still have this bias relative to OLS interpretation. But n is equal to 1, the bias criterion is going to be the same as in Montiel-Lee and Pfluger. So to go back to that earlier question about tau, so when you're choosing tau here, you're thinking about the bias of two-stage least squares relative to the worst bias you could possibly get from a two-stage least squares estimator. So it actually becomes, I think, from my perspective, to be completely honest here, even harder to think about choosing an appropriate tau here, maybe, than it is in the Stark and Yogo setting, because you're thinking about bias relative to how bad two-stage least squares bias can possibly be. So choosing a threshold there is a pretty, I think, I would admit, it's a pretty arbitrary distinction, but the literature seems to have settled around the 10% level. Right, so now we know what it means to have weak instruments bias, and we can quantify that. We can define when instruments are indeed weak. So we're going to define the set of models with the set of instruments that we consider to be weak as a set of models where the bias criterion is going to exceed this relative level, this threshold tau, right? The bias relative to the benchmark is equal to tau. is greater than or equal to tau. But the trick here, and as I say, in an applied practice, tau is usually set equal to 0.1. But the trick here is that this set is going to be indexed by W, which is this application-specific, or indeed regression-specific covariance matrix, which you can consistently estimate. However, there's also going to be nk plus n nuisance parameters that you need that go into determining whether your set of instrument, whether your particular model falls into this set of models for which we say the instruments are weak. And these, of course, cannot be consistently estimated, right? If we can consistently estimate beta, we don't have a weak instruments problem to begin with. So this is actually quite tricky. There's a further complication here, which is that the expectation of beta star, which of course, if we go back, enters the bias criterion as well, isn't available in closed form. So what Stock and Yogo do is evaluate this numerically. This is not that, it is much easier in Stock and Yogo because there's no dependence of this set on W, right? Beta tau there is constant with respect to the covariance matrices because, you know, everything simplifies very nicely under homoscedasticity. So in their setting, this is something the econometrician has to do only once when writing this initial paper where you compute all these tables. Basically, you know, set up a bunch of, you know, grids for the nuisance parameters, and you can do this numerical integration, and you can kind of find the relative thresholds for the weak instrument sets that we'll talk about a little bit later. But in our setting, using numerical integration to evaluate this weak instrument set, besides the nuisance parameters here, would have to be done every time you specify a new first stage regression, which from a computational perspective for an applied user is never going to be an attractive proposition. So we're going to have to do something a little bit different here. What we use is going to be the Nagar approximation for the bias, which is going to be the same technique adopted by Montilia and Fluger. So with the Nagar bias, if you denote as B sub n, it's going to be the expectation of a second order Taylor approximation to the distribution of beta star, that's a deviation between the two safe least squares estimated and the truth, taken around the means of the underlying random variables. So the first main result in the paper is theorem 1. And the first part of, you know, the actual contribution isn't even kind of, you know, in the main text of the paper. It's actually to work out what the Nagar bias is in this more complicated setting, to actually work out expressions. So, you know, that's a significant endeavor in its own right. But the important part for the paper is actually providing the worst case Nagar bias, which is an upper bound on the Nagar bias, and indeed two different sets of upper bounds on the Nagar bias. Because ultimately, as I mentioned before, the weak instrument set depends on all of these nuisance nk plus n nuisance parameters in C and in beta. So we can't consistently estimate them. So as an econometrician, you have to think about the worst case bias you could achieve, that could be achieved over the possible values for those parameters. So the first result, part I here, is providing a sharp bound for the Nagar bias here, which we denote as B star sub n. And we show that this has two different parts. The first, script B of W, is going to be the supremum over essentially a function of matrices of zeros and ones and functions of W, which can be consistently estimated, and orthogonal matrices L0. So essentially, this is just an optimization problem. It gives you script B of W. The optimization problem only depends on things that can be consistently estimated. Those are elements in W. The second part is just the minimum eigenvalue of the concentration matrix. So this sharp upper bound on the Nagar bias is script B of W divided by this minimum eigenvalue. I'll talk a little bit more about that important structure on the next slide. We also provide a second set of bounds in the paper, which are going to be our simplified bounds. These bounds are not going to require any sort of optimization problem. You can see they don't depend on the supremum of anything. They depend simply on this formula that is based on W, which is consistently estimated, and essentially matrices of zeros and ones. So you can compute those instantaneously, whereas the first set do require an optimization step. But let's look at that in a little bit more detail, in particular that sharp bound. So it has this form of script B of W, which is an optimization problem divided by a minimum eigenvalue. So to be clear, again, this is the worst case Nagar bias, which is going to allow us to abstract from all of those nuisance parameters that I mentioned a couple slides ago, except for this one minimum eigenvalue, the concentration matrix. But the key here is that script B of W will be able to be computed very quickly, because while it has an optimization problem, it's just an optimization problem over the space of orthogonal matrices. Thankfully, we're not the first people to study optimization over the space of orthogonal matrices. So there are some exceedingly well-optimized algorithms available from the statistics and computer science literature to do exactly this. So for standardized problems, this is done in a tiny fraction of a second. So you can view this as essentially being an instantaneous calculation for these bounds. However, for very large problems, and we've been in touch with some empirical researchers already who are working on such problems. So think about having, say, 100 instruments. The dimensions start to get a little bit larger. The problem starts to be a little bit less well-disciplined. And this optimization step starts to take an hour or two as these models get very large. In that case, you might want to think about using the simpler bounds, which are going to be more conservative, but will sidestep these kind of computational burdens, at least maybe for preliminary explorations, right? When you're running your final regressions for a paper, maybe you're fine waiting an hour or two to compute critical values. But for the purpose, for some purposes, these simple bounds may be appealing. So now we have a way to measure the worst case Nagar bias for a given matrix W that you consistently estimate that depends on a single nuisance parameter, lambda min, the minimum eigenvalue of the concentration matrix. So now we need some sort of test statistic that depends on exactly this sufficient statistic. And ideally, what we want to do is be able to test whether this quantity, this minimum eigenvalue, exceeds some threshold, lambda min star, which is exactly the level at which the worst case Nagar bias would be equal to the tolerance level tau. So we want to test whether we can exceed this level, lambda min star. So what we're going to do, what the test statistic that we're going to use, as I introduced previously, is going to be G-min, which is going to be the minimum eigenvalue of a rescaling of the denominator of the two-stage least squares estimator, or rescaling of the Krag-Donald statistic, where the rescaling is this phi matrix, which has this special structure we've discussed a couple of times already. So far, so good. Then we have to work out the limiting distribution of this test statistic, and that's where things start to get more complicated. So it's going to depend on an NK by NK random non-central Wishart random variable, zeta, which is what you see in the middle of that expression there. Non-central Wishart random variables are not the friendliest to work with distributionally to begin with, but it's not going to depend just on zeta. It's going to depend on that special structure again. So for an NK by NK non-central Wishart matrix, it's going to depend on the N by N matrix of traces of each of the K by K partitions of that non-central Wishart random matrix. But then it's again going to depend on the minimum eigenvalue of that N by N matrix of traces. So this is a very non-standard limiting distribution, to say the least. So for anyone who's kind of losing hope in how we're kind of getting anywhere here, given the complications in the limiting distribution, just to kind of give you an idea of where we're going, the matrix of traces of the K by K of each of the K by K blocks of the non-centrality matrix of zeta is actually equal to just K times the concentration matrix. You can see if we can learn something about the non-centrality parameters of zeta, that's going to be, and indeed the minimum eigenvalues of the non-centrality parameters, that's going to be informative for the non-centrality, for the concentration matrix lambda. So as I've said on the previous slide, G-min is going to converge to the minimum eigenvalue of an N by N matrix consisting of the traces of each of the K by K subpartitions of a non-central Wishart matrix. We don't know what this distribution is. What can we do in this setting? We're going to start by using a trick straight out of Stock and Yogo, which is to note that for some unit vector gamma prime times A times gamma, for any unit vector gamma prime times A times gamma is an upper bound on the minimum eigenvalue of the matrix A. So we care about the minimum eigenvalue of this matrix of traces. What we're going to work with instead is an upper bound on that minimum eigenvalue, which is going to be gamma prime times this matrix of traces times gamma. This is the second main result in the paper, in which we provide expressions for arbitrary cumulants of this bounding random variable, and will indeed provide some bounds on those cumulants. So the first part of the theorem drives exact expressions for the cumulants for this upper bound on the minimum eigenvalue of the variable of interest. The second part of the theorem, but you'll note in part I, right, we still have dependence on all of the all of the elements in the non-centrality parameter, so non-centrality matrix, the eigenstructure of that matrix, not just on lambda min, which is the minimum eigenvalue of the concentration matrix. We also have dependence on gamma, which is this, unknown vector. So the second part of the theorem is to work out upper bounds for these cumulants. And indeed, when you look at the upper bounds there, you'll see that actually we've abstracted away from gamma, and we've also been able to remove the dependence on the eigenstructure of the concentration matrix. So now these upper bounds depend only on the minimum eigenvalue of the concentration matrix, which is indeed exactly the sufficient statistic for the bias criterion that we laid out before after adopting the Nagar approximation. So now we have kind of expressions for properties of the limiting distribution, the cumulants, that depends on exactly the sufficient statistic that we're interested in. If the covariance matrix W has the Konica structure, as in Stock and Yogo, these cumulants actually collapse exactly to those of the non-central chi-squared distribution, which is the limiting distribution that holds the Stock and Yogo test statistic. So we have cumulants, we still don't have critical values. How do we get to these critical values? We're going to use the approximation for limiting distribution that kind of has this sort of chi-squared-like, Wishart-like structure that's due to Imhoff, that's kind of been fairly well studied in kind of this statistical approximation literature. So essentially, you just manipulate expressions for the first three cumulants and the quantiles of chi-squared distribution to find an approximating distribution that generally has been shown to well approximate the behavior of these types of random variables. I will say that this approximation step is the one step of our procedure that is not inherently conservative, where it's possible that you might have some non-conservative approximation error built in. Although in our simulations, we have kind of no evidence to suggest that is happening to a problematic extent. However, you may think back to the cumulants that we just derived and remember that actually our ultimate expressions weren't the cumulants themselves for the random variables of interest, were actually upper bounds on the cumulants of interest. And of course, there's no guarantee necessarily that using upper bounds on the cumulants is going to be accurate or indeed conservative. So what we show in the paper is that using upper bounds on these first three cumulants, as opposed to the true cumulants for Imhoff approximation, is going to be conservative for the approximation based on true cumulants for percentiles far enough in the right tail. But this sounds a little bit hand-wavy, right? What does far enough in the right tail mean? Well, just kind of give you an idea numerically, for models with kind of normal numbers of instruments, right, up to say like 20 instruments, provided you're looking at the 5% critical values, you're never going to end up with a non-conservative approximation. If you're trying to think about, say, 10% critical values, so not so far on the right tail, or a very large number of instruments, then perhaps you might end up with the cumulants, the upper bounds on the cumulants no longer providing a conservative approximation. What the code we provide does in practice is check some Kuhn-Tucker conditions to ensure that the cumulants that the upper bounds in question do turn out to provide a conservative approximation. If they don't, we solve for cumulants that do satisfy these Kuhn-Tucker conditions to ensure conservativeness. So in practice, the critical values that we obtain will always be conservative in this respect. We're not going to end up with any anti-conservativeness coming from not using the true cumulants here. So the end result is going to be a bounding limiting distribution for the test statistic that depends only on the minimum eigenvalue and reduced form estimates found in W, this covariance matrix. So to summarize what we've just done, first, we had to define what weak IV bias meant in this setting. And we did that by using a weighted L2 norm of the bias of two-stage least squares relative to a benchmark. This bias criterion netted both Stock and Yogo in the case of homoscedasticity and Montiel-Lee and Pfluger in the case where n is equal to 1. We argued that G-min was going to be a sufficient test statistic because after using the worst case Nagar approximation, we were able to show that the weak IV set was indexed by a single scalar nuisance parameter lambda min, but also that the test statistics limiting distribution depended on this exact same sufficient statistic. The distribution of G-min turned out to be quite challenging, but we're able to derive a bounding approximating distribution by working A with an upper bound on the minimum eigenvalue of the random variable of interest, and then upper bounds on the cumulants for that random variable. We also argued that to have a test that would be usable in practice on the same scale as the Stocking-Yogo test, we'd have to be able to compute critical values pretty quickly. We can do that because the Nagar approximation reduces the problem to, for the sharp bounds, only searching over the space of orthogonal matrices, for which there are very specialized optimization algorithms, which are lightning fast. So just quickly, I want to show you what these critical values look like in practice. And for the most part, there's not going to be too much to learn here, but we can kind of speak to some of the issues that have come up in the paper, come up in the presentation so far. So our critical values, our main critical values are going to be in blue, and our simplified critical values are going to be in red. These are the ones that use the more conservative bound that doesn't require optimization. In purple, you can see the critical values from Montiel-Lee and Pfluger. I should mention that what I'm showing right here is the n=1 homoscedastic case. So both Montiel-Lee and Pfluger and Stocking-Yogo are valid here. In yellow, you can see the critical values from Stocking-Yogo, and in green, you can see some more recent critical values for Skeels and Windmeijer that are computed analytically. You can see that our critical values agree, with one exception, perfectly with those from Montiel-Lee and Pfluger, and the Stocking-Yogo critical values agree perfectly, essentially, with those from Skeels and Windmeijer. So, those are the first thing I want you to note. However, that you can also start to look at the difference between using the Nagar approximation and using numerical integration. So the wedge that you see between those two sets of critical values, that's essentially the difference between using numerical integration or having an analytical expression in the case of Skeels and Windmeijer and having to resort to the Nagar approximation. You can see that there's some deviation. How large is it? I would say it's not too large, and it's necessary to make a practically feasible test in our setting. We'll talk a little bit more about this though in the simulation section. I want to touch on this one deviation from Montiel-Lee and Pfluger, which is which occurs when there's an over-identification of degree 1. When there's over-identification of degree 1, the Nagar bias is mechanically 0. So you cannot really use these expressions for the Nagar bias to propose a reliable test here. This is something that's not recognized in Montiel-Lee and Pfluger. What we propose doing instead in this setting is using our conservative, our simplified critical values, which still are tied to the Nagar approximation, but in simulations actually turn out to control bias quite well. Won't have time to show that here, but it's in the paper. Under heteroscedasticity, we can't show Stocking-Yogo critical values aren't going to be valid here. We can still compare to Montiel-Lee and Pfluger. One thing to note, these are now going to be application-specific critical values. So what we've done is drawn 500 random W matrices and taken the average critical values across all of them. So there's going to be this is going to mask differences that across W. This is trying to show you the average tendency. We're always going to agree exactly though with Montiel-Lee and Pfluger, except for this one case that I've mentioned before. But what I want to show you here is actually that on average, with heteroscedasticity, there's not this giant wedge anymore between the simplified critical values and our sharp critical values, although there's always kind of some positive difference between the two critical values because they're conservative critical values, the simplified ones. Finally, next, with multiple endogenous regressors under homoscedasticity, you can compare to Stocking-Yogo, but not Montiel-Lee and Pfluger, because they don't allow for multiple endogenous regressors. Here you can see once more that our critical values are very close to those of Stocking-Yogo, which are also valid in this setting. So again, there's not a huge loss here using the Nagar approximation. Here you can see, though, that there's still, there's again a wedge between the simplified critical values and the sharp critical values. Finally, the case where our test really shines is with heteroscedasticity and multiple endogenous regressors, where there's nothing to compare it to. So there's not much to take from this slide, except we can compute these critical values, whereas the previous tests are not valid in this setting. You might be tempted to say, oh, well, it seems like the average critical value here is about 15 or 16. That's larger than the critical values in Stocking-Yogo. So you're always going to be you're always going to be over-rejecting using stock and Yogo. But that's not really a comparison you can make, because it's really an apples and oranges comparison. So test statistic that is compared to these critical values is different, right? It's a rescaled version of the test statistic in stock and Yogo. So you can't kind of make those sorts of inferences here. So now I can move on to our simulation study. We're going to try to do three things in the simulation study. First, we're going to look at the size and power of our test with respect to determining whether weak instruments bias is present. We're also going to look at the scope of the pre-testing problem here that I mentioned a little bit in the introduction. Try to look at the properties of post-test inference for beta using simple T statistics, which is the topic of a recent paper in the AAR by Lee et al., which really focuses on how distorted these t-tests following a pre-test could be in practice. Third, we're going to look at something we've talked about already, which is the quality of the Nagar approximation. So to do this, we're going to look at a variety of different n and k in the paper. I'm going to focus just on n equals 2, k equals 4 for the purposes of this presentation. We're going to look at 5 million randomly generated DGPs, right? We want to be as exhaustive as possible here. And for each DGP, we're going to take 1,000 samples. We're going to do this. So half of these 5 million DGPs are going to be drawn completely uniformly. Half of them are going to be drawn slightly more cleverly in the neighborhood of the worst case, just to kind of give the test a little bit of a harder time here, make things a little bit more interesting. So first, let's look at the size and power of the test. So this is going to be a little bit of a different plot many people are used to looking at, so I just want to explain what's going on here. We've got 5 million DGPs. For each DGP, you can compute a power curve. Essentially, this is plotting each power curve instead as a scatter, and now we're going to look at kind of the collection of power scatters across 5 million DGPs. So it's kind of like an envelope of power curves. You can kind of think of it. So in red, that's the cloud that I really want you to focus on, which is going to be plotting the worst case Nagar bias, which is the quantity that our test is supposed to control, against the rejection rate. Now, if this test was perfectly sized, so if it was going to, it is going to erroneously reject exactly 5% of the time when instruments do turn out to be indeed weak, you'd want to see the power curves pass exactly through the intersection of those two black lines. So you can see that the upper envelope, right, of this collection of power curves, passes very close to that intersection, right? So we're controlling size reasonably well at the upper end, although the tests are conservative, because you do see rejection rates certainly at that threshold of 0.1 that are well below 0.05 as well. However, while we're conservative, we're not prohibitively conservative, because you can see that the power rises quite sharply to the left of that. Essentially, as soon as you get to, say, bias of 0.05, when your test is designed for a bias of 0.1, you're getting non-trivial rejection rates that are rising quite sharply towards 1. So while we're conservative, we do have non-trivial power before you travel kind of too far to the left of 0.1, which is that value for tau that we're calibrating to. What we're also showing here is a separate set of power curves, or power scatter for the relative to the Monte Carlo bias, as opposed to the worst case Nagar bias. In practice, you can't compute kind of the true bias of a particular DGP because you don't know the nuisance parameters, right? That's why we're working with the worst case bias in the test, because you don't know the values for C, you don't know the values for beta. But in a simulation study, we can compute the actual Monte Carlo bias for each DGP, and just to kind of confirm the conservativeness of the test further, and indeed the fact that our bounds are accurate, we wanted to look at this, and you can see that yes, you're indeed more conservative when you look at the Monte Carlo bias as opposed to the worst case bias. But of course, the test is designed not to control Monte Carlo bias, but it's designed to control the worst case bias. Next, we can look at the Nagar bias versus the Monte Carlo bias, and in particular, the log of each of these two quantities. And if the Nagar bias was perfectly accurate, this would just be a 45-degree line. What you can see is, generally speaking, it's close to the 45-degree line. The region of interest, which is kind of values for the bias between 0.05 and 0.15, is what's in that intersection of dashed black lines. So you can see that within that region of interest, they're fairly close to that 45-degree line. There is a bend away from the 45-degree line, though, in this cluster. The reason for that is, of course, that there's a sharp upper bound on the Monte Carlo bias, right? Because it's the bias relative to a worst-case benchmark. You can never be worse than the worst-case benchmark, so you're bounded above at 1. The Nagar approximation, however, does not always respect that bias that holds in the true integral. So the Nagar bias can be a little bit higher. So that's why you get this kind of bending property to the top right. But thankfully, it's not too severe in the region that we care about. Finally, we can speak a little bit to this pre-testing problem, as I promised. So we're going to plot here is for given value of G min, we can compute the rejection rates of T statistics for the elements of beta. And you can plot the distribution or summary of the distribution of those test statistics for different values of G min test statistic. So what the shaded at, so the blue line is the median. The shaded region is going to plot between the 2.5 and 97.5 percentiles of these rejection rates. So what you don't want to see is essentially for values to the right of that vertical line, rejection rates too far over 0.05, because that says that you're actually going to have a severe pre-testing problem, right? Conditional on passing the pre-test. You're going to over-reject the null hypothesis when you go to do inference on the structural parameters of interest. Now, thankfully, what we see here is this upper end of this 97.5 percentile is at the threshold of G min equal to the critical value, only equal to about 11%, and kind of falling away fairly sharply off after that. So given that when you have size-based tests, often their tolerance for over-rejection is about 5%. So you'd be looking at allowing up to a 10% rejection rate. This isn't a terrible amount of over-rejection. This contrasts to some of these recent papers in the literature that I mentioned, which show very large over-rejection due to the pre-testing problem. The vast majority of these papers, though, only study the case under homoscedasticity with n equals 1 and k equals 1, a single endogenous regressor and a single instrument. So our hypothesis, with nothing rigorous to back this up so far except some simulation studies, is that actually may be the worst case in terms of this pre-testing problem and over-rejections. We have not found rejection rates to be anywhere near that large in these more general settings. We don't have anything kind of more formal to discuss that, really.
Daniel, can I make a very quick comment here or question? So in the stock and yoga results, so the size distortion is very much dependent on the endogeneity level. Yeah. So the correlation of the residuals. So if that goes close to 1, that's when you get your large critical values. So sure. How do you control for that here?
So, I mean, this is over 5 million DGPs, where we've drawn a lot of DGPs that will be in that region. So I guess your point is interesting, though, in that, those DGPs, all of the DGPs with really high endogeneity, like those you mentioned, maybe in that extra 2.5% that's outside of this interval. That's a fair comment.
Yeah. So you average here overall values of rho, basically.
If you want to be fully uniform, right, this is probably not the exercise to show you. Yeah. Looking at the correlation between these rejection rates and the correlation between U and V, the degree of endogeneity, is something that would be interesting to add, so I could speak a little bit more concretely to your comment. But okay, that's a fair point.
Thanks.
Okay, in the final 5 minutes, I'm going to talk very briefly about an empirical application. So we're going to study Remy and Zuberi's recent analysis of regime-dependent cumulative government spending multipliers, where they're using local projections in the Journal of Political Economy. The idea here is you want to estimate the effects of government spending depending on the state of the economy. So they have 2 instruments for government spending. One is based on Blanchard and Peroty's shocks. The other is based on defense spending news. You have government spending as a single endogenous regressor, but once you interact it with an indicator for the state of the economy, of course, you then have 2 endogenous variables. You also are going to have 4 instruments because you're interacting the instruments with the state of the economy. So what do they do in this paper? Well, they're very careful about the fact that you often have serious heteroscedasticity and autocorrelation, particularly with these types of shocks and in these longer horizon local projections. So they use the Montiel-Lilian-Pfluger test regime by regime, right? You have an interactive regression. It's kind of like estimating, point estimate wise, you can think about this as estimating 2 separate regressions. You test whether each of those regressions is separately strongly identified. What we can do is formally test the fully interactive model jointly. So we look at 5 different specifications from Ramey and Zubri. We're looking at different subsamples and different indicators for the state of the economy. The first is a measure of slack based on the unemployment rate, the other based on whether the economy is at the zero lower bound. What we're going to do for each, right, we're going to look at each horizon of local projection, they estimate separately, and plot the difference between a test statistic and the critical value. Positive value means you reject weak instruments, negative value means you fail to reject weak instruments. We're going to plot the Stock and Yogo test for comparison, even though they don't study this in their paper. What you can see based on the Stock and Yogo test in red is that for 3 of the 5 specifications, you're able to reject the null of weak instruments at all horizons. The other 2 you can reject kind of at the first half of the horizons. Using our test, on the other hand, you fail to reject the null of weak instruments for any of the specifications after the first few horizons. And indeed, for a couple of the specifications, you only reject for the first 2 horizons. So the conclusions are meaningfully changed. Essentially, there's almost no relative, I don't say almost no, but very few horizons for which you're strongly identified based on our test that respects the heteroscedasticity and autocorrelation in the data. An interesting comparison is between what you'd learn regime by regime using Montiel and Pfluger's test, which is what they use in the original paper. Now, I've mentioned, of course, how our test statistic, right, nests the Montiel and Pfluger test statistic as a special case. And indeed, if you're getting the same point estimates, and we have essentially the same bias criterion, you'd expect the conclusions to be very similar to those based on Montiel and Pfluger. Indeed, that is the case. So essentially, the result of our test is governed by the more weakly identified regime based on the regime-by-regime Montiel and Pfluger test. So essentially, if one regime is strongly identified according to Montiel and Pfluger, the other is weakly identified, our test will tell you that the whole model is weakly identified, which I think makes sense, given that we're using same point estimates and essentially a bias criterion that nests theirs. One caveat is that our test is very marginally more conservative. So there are a few knife edge cases where you may be just above the threshold going regime by regime for both regimes and just below the threshold using our test. The reason for that is when you go from n equals 1 to n equals 2, you have to use an additional level of approximation to compute the limiting distribution. Remember, you need to compute the minimum eigenvalue of the limiting random variable. We had to use an upper bound to do that, as opposed to the true minimum eigenvalue. You don't have to worry about minimum eigenvalues when you have a scalar to begin with. So that's the one realm in which the conclusions would change in this particular setting, given the structure of the problem. So to conclude, what we've done in this paper is generalized the Stock and Yogo test and extended the Montiel and Pfluger test to finally have a fully general test for weak instruments, is robust to heteroscedasticity and autocorrelation, and allows multiple endogenous regressors. We've been able to nest both of those existing papers as special cases throughout. The key to doing this was using the Nagar approximation, under which the worst case bias depends only on the scalar sufficient statistic, which is the minimum eigenvalue of the concentration matrix, and the asymptotic covariance matrix of the first stage coefficients, which we can consistently estimate. The test statistic had a very difficult limiting distribution to work with, but we're able to work out bounds on its cumulants that depended only on this same minimum eigenvalue, and W2, and then we're able to use the Imhoff approximation to arrive at the critical values. These critical values are going to be conservative, but our simulation evidence, I think, shows that they're not prohibitively so. And of course, they're very fast to compute in practice for most models, which is going to be crucial in terms of adoption and actually getting people to use these sorts of procedures. The performance we've seen in the simulations review is quite encouraging, and I think there are many sorts of applications where these will be very useful going forward, and indeed, we've had a lot of people eager to use the test already. So thanks so much for your attention and some interesting questions already, and I look forward to discussing further.
Thank you very much, Daniel, for this excellent presentation. So I think we're going to stop now the recording.